Hey, today we will prove Bökstedts theorem computing the topological Hochschild homology of Fp. We will deduce it from an interesting statement about the dual Steenrod algebra as an E2 algebra, and that will also teach us something about Dialashov operations. I'm Achim Krause from Mathematics Münster. Bökstedt periodicity refers to Bökstedt's theorem computing the homotopic groups of THH of the field Fp. More precisely, Bökstedt proves that the topological Hochschild homology groups THH star Fp are as a ring, using the ring structure that you get on THH, since Fp is a commutative, HFP is a commutative algebra in spectra. As a ring, this is given by a polynomial algebra on a generator in degree 2. So this is what we want to prove today, but it turns out there's a slightly nicer way of phrasing this, an equivalent way of phrasing this that doesn't just talk about the homotopic groups of THH-Fp, but actually about the spectrum THH-Fp. So what is this variant? Let me call this Bökstedt's theorem version 2, since this is really just a restatement, as we will see. So here the statement is that THH-Fp is as an E1 algebra over HFP, free on one generator. And another way to say this is that THH-Fp is equivalent as an HFP algebra to the HFP algebra that you get by taking the E1 algebra loops S3 in spaces, in pointed spaces, and then taking sigma infinity of it, and then tensoring with HFP. So here's a couple of little remarks I need to make about this in order for it to make sense. So first of all, why is THH-Fp an HFP algebra? Well, if you think about the definition of THH of an ordinary ring, then we defined this as the cyclic bar construction applied to the Eilenberg-MacLane spectrum associated to that ring. So THH-Fp is simply the cyclic bar construction, or rather the co-limit of the cyclic bar construction on HFP. And you have a map from HFP into that, simply as, so to say, the zero simplices. So this endows THH-Fp with the structure of an HFP algebra. And of course, it is actually a commutative algebra. So it's an E-infinity algebra, but we're looking just at the underlying E1 structure, right? So this is a statement where we forget some of the structure. And then the second thing I need to say is, why is this over here another description of the free HFP E1 algebra on one generator, sorry, I should have said here, on one generator of degree 2? Well, recall that, maybe write something down here, recall that loops sigma S2 is the free E1 algebra on the pointed space S2. This comes from the so-called recognition theorem of EN algebras. And once you know that, well, you can check that maps out of an E1 algebra over HFP HFP tensor sigma infinity loops S3 into another E1 HFP algebra. So first of all, let me say that first, maybe this expression that we get by applying a certain functor to this E1 algebra in spaces. And what is that functor? Well, it's taking sigma infinity and then it tensors with HFP. So it turns out this is a symmetric monoidal functor from pointed spaces to well, HFP modules. So it takes this E1 algebra in spaces to an E1 algebra in HFP modules, meaning an HFP E1 algebra. So this makes sense. This is an E1 algebra over HFP. And then by a chain of adjunctions, this is, first of all, simply the same as a map of just E1 algebras loops S3 to loops infinity R, where this is endowed with an E1 structure due to the Lex symmetric monoidal structure of omega infinity. And then further by this assertion here, that this is the free E1 algebra on S2. This is simply the same as just maps of spaces, or I guess pointed spaces, S2 into loops infinity R. And then finally, this is the same as just HFP module maps from, well, HFP tensor that by an adjunction between, well, I guess we're using, let me do that in two steps. This is maps of spectra, sigma infinity S2 into R, and then finally maps of HFP modules HFP tensor this, so in other words, just sigma 2 HFP into R. Right, so this is a chain of adjunctions, but it tells you that giving an E1, like a map of E1 algebras out of this guy is simply the same as giving like either an element in pi 2 of R or I guess such a module map. Right, so this is what we mean when we say that this algebra is free on a generator of degree 2. But maybe the nicer way to think about this is really just saying that it's equivalent to this guy. And what does this tell us? Well, let me prove, before we prove either of the versions of Bökstedts theorem, let me really just prove that those are equivalent to get some feeling for why this is a good reformulation. So let me write like proof of equivalence here. This is a proof that both versions of Bökstedt's theorem I gave are equivalent. So the element x in THH2 of Fp that we constructed previously, where we said that somehow in degree 2, THH and ordinary Hochschild homology still agree. So we had a preferred element of this, and we knew already that this group was Fp. So this defines an E1 map, so a map of E1 HFP algebras from this algebra HFP tensor sigma infinity of loops S3 to THHFP. And this map is an equivalence if and only if the statement about the homotopic groups of THH that the first version of Bökstedt's theorem amounted to is true. So if this is polynomial on this element x. Well, why is that? Well, to see that, we simply need to check. So this map, by construction, takes a certain element in degree 2 here, in pi 2 of this guy, to the x here. So if we knew that pi 2 of this guy has this form, it's polynomial on a generator of degree 2, then, well, this map is an isomorphism on homotopic groups if and only if the right-hand side also has just this polynomial algebra on x as homotopy, right? So what we're saying here is that, or said differently, if you know the first version of Bökstedt's theorem to hold, that this is polynomial, then simply by computing the homotopic groups of this guy to also be polynomial on the degree 2 generator, you can check that this map is an equivalence, because equivalences are detected on homotopic groups. And so what are the homotopic groups of this? Well, it turns out that if you take a spectrum and you tensor it with HFP, and then you compute its homotopic groups, you're getting the homology groups of the spectrum you plugged in. So in particular, what we're saying here is that the homotopy of this guy over here agree with the homology groups of loops S3 with coefficients in Fp. So this assertion that the homology groups of a space agree with the homotopy groups of the spectrum you get by taking sigma infinity and then tensoring with HFP, I want to pose that as an exercise. So the idea is that you can just check that this construction here defines a homology theory, and you can check that it satisfies all the Eilenberg-Steenrod axioms, so it has to agree with singular homology. I think that's a very good exercise if you've never seen this relationship between spectra and homology theories. So, having said that, what is this? Well, this is something you can compute with the Serre spectral sequence. You can compute this to be Fp in every even degree. And I'm not going to do that here, but it's sort of a straightforward exercise with the Serre spectral sequence. And it turns out that the E1 algebra structure you have on loops S3, right? That's what corresponds to the product structure over here. That gives this homology, the so-called Pontryagin product, that turns this into a polynomial algebra. So this is, I would say, like a kind of very classical computation. So what we see here is that the homology groups of this guy are polynomial, and so this map is an equivalence if and only if we know the homotopic groups of THH to be polynomial. So the two versions of Bökstedts theorem are equivalent. Also note that we're saying here that the free E1 algebra on a generator of degree 2 has this nice property that its homotopy groups, the free E1 algebra over HFP with a generator in degree 2 has this nice property that its homotopy groups are really the free graded algebra on a generator in degree 2. So that's a very nice fact that still works somehow for associative algebras, for stuff like commutative algebras, or more generally EN algebras. The homology, of course, will be more complicated. But essentially, this is something we're using here for associative algebras. So in order to get at THH, right? So we want to prove the second version of Bökstedts theorem now. In order to get at that, we will have to give a slightly different perspective on THH. This is similar to something we did for Hochschild homology earlier. Namely, we're claiming that for an arbitrary ring spectrum R, THH of R can be written as this funny tensor product, where here I put R tensor R op, but now this is tensored over the sphere. And this guy acts on R both as a left and a right module. This comes from the bimodule structure that these guys have. And so you can tensor them, and the claim is that this gives you THHR. And let me give a proof sketch. And the proof sketch is similar to what we did for Hochschild homology when we proved the corresponding statement there. Namely, the idea is that we write R as R tensored over itself with itself. Right? This is kind of the usual fact that if you tensor something over, like if you tensor with a ring or over a certain ring with a free module of rank 1, you don't change anything. But if you remember how we defined this as some kind of realization of a bar complex, right? So this is not as tautological as it sounds or as it looks like. We defined this as colimit of this kind of simplicial diagram. Right, for general tensor products, we somehow had this bar construction with like copies of the ring in the middle and copies of my modules on the left and right. Here we do the same with like all copies given by R. And so this is an interesting way of writing R itself as a colimit of things that are not R, right? This is not a constant diagram. And it turns out this is actually a diagram of RR bimodules, right? On each guy I can act with R on the left and with the rightmost R guy on the right. So we have successfully decomposed R as an RR bimodule into these kinds of pieces. And now if we just apply this functor that takes like a bimodule and tensors it over R with this, then what we get is that R tensor over this R tensor R op guy with itself So we simply write the second factor as this colimit, use that tensor products commute with colimits, and we see that this gives me like a colimit over delta op of terms that are of the form R tensored over R tensor R op with then the stages of this diagram, right? So each level is, in level S, I have something that looks like an S+1 fold tensor product of R. And now if we look at this, then what we're doing here is if you think about how this tensor product works, it identifies the leftmost and the rightmost R factor into one R factor, right? It identifies them with each other. And so this construction here turns this simplicial diagram into one where we've kind of identified the rightmost factor in each degree into the leftmost factor. And then if you think about what the simplicial structure of this is, you see it's exactly the cyclic bar complex, right? So this kind of construction, it turns this two-sided bar construction into just the cyclic bar complex. And in particular, this is simply THH, right? And of course, that's just a proof sketch, because again, we can't, in this infinity world, we can't really manipulate these things just on the level of objects. Usually you would have to kind of put all that combinatorics into some machinery. But this sketch gives you a pretty good idea of what to expect. And also note, although I'm not going to do that, you can also get a description like this for the version of THH with coefficients in a bimodule, right? There was this version where you have copies of a bimodule M, like one copy in each degree, and you can similarly obtain, like from this two-sided bar construction, you can put your bimodule in there for one of the factors, and then this proves that THH with coefficients in a bimodule can also be written in this kind of tensor product way. So if we want to apply this tensor product style description of THH to FP, then we need to understand HFP tensored over S with HFP, right? And a priori, this should be incredibly hard to understand, right? If you come at this from like a perspective of thinking about the homotopic groups, then you already don't know the homotopic groups of the sphere, right? And these are somehow going to influence what you get here. This is not just going to be HFP. So this looks pretty difficult, but in fact, this is something that's pretty good understood by algebraic topologists. This is, if you remember what I said about tensoring with HFP and then taking homotopy, you can interpret the homotopy groups of this as FP coefficient homology groups of the Eilenberg-MacLane spectrum HFP. So this is closely related to understanding homology or cohomology of Eilenberg-MacLane spaces, and this is something that topologists have done. And in particular, we understand the homotopy groups of this as a ring. And so this description of the homotopy groups of this guy as a ring, that's due to Milnor. So in this context, this is known as the dual Steenrod algebra. And he has a pretty nice paper on that. I suggest to check that out. It's very nicely written. And it turns out that this has a surprisingly straightforward structure. So there's kind of a slight difference for p equals 2 and odd p. related to the usual fact that somehow you don't have to think about graded commutativity in characteristic 2, but at all other primes. And so if p equals 2, the answer is very straightforward. It's just that this guy is polynomial over F2 in infinitely many generators, zeta I, starting with zeta 1 and so on. And the degree of zeta I is 2 to the I minus 1. So these are generators in degree 1, 3, and so on. 1, 3, 7, and so on. So for p odd, this is a little more funny, coming from the fact that some generators are now in odd degrees. So there's a part of it that's an exterior algebra on generators tau 0, tau 1, etc. And a polynomial part. It is an exterior algebra over Fp, and then you have a polynomial part on generators xi1, xi2, etc. And again, you can determine the degrees of those, and they are 2p to the I minus 1 for the taus. So the tau 0 is in degree 1, and then they kind of go up exponentially. And the xi's are 1 degree smaller, 2p to the I minus 2. So that's, of course, somehow pretty big algebraically, but it's surprisingly clean, right? If you think about homotopic groups of the sphere instead, it's a super messy ring and we don't fully understand it and never will. But this is somehow something you could expect to algebraically control. But of course, this is still pretty big. And so here's a surprising different description of not the homotopic groups, but directly of the spectrum. And this is kind of similar to what we did for THH in the reformulation of Bökstedts theorem. So again, this guy, HFP tensor HFP, has an E-infinity structure. This has the structure of a commutative algebra coming from the fact that you've just tensored two commutative algebras together. And it's even a commutative HFP algebra, right? Because HFP maps into this. You have to be a little careful because you can put two different HFP algebra structures on this. And in this higher algebra world, there's no reason why two different HFP algebra structures on the same ring should agree. Different from the fact that somehow FP algebra structures in algebra are unique if they exist, right? They're just a statement that everything is killed by multiplication with P. But here, you have to be a little careful, and you should think of this as the fact that somehow Fp has a simple presentation over the integers, but not over the sphere. And that's the base ring we're working over, right? So HFP as an S algebra has somehow a complicated description in terms of generators and relations. So we need to make a choice here, and let's say we view HFP tensor over S, HFP as HFP algebra via the inclusion of the right factor. It's simply a convention you're meeting. In fact, this guy has an automorphism that switches the two factors. So these don't qualitatively differ. So the statement we will now make, the following lemma, it's kind of the crucial part what goes into Bökstedts theorem. It's much more subtle because now in Bökstedts theorem we had an E-infinity algebra, this let me put that here. It's an E infinity HFP algebra. In Bökstedt's theorem, we had an E infinity HFP algebra, and we just viewed it as an associative algebra and said it is free as such. Here, we want to look at this as an E2 HFP algebra. And the claim is that this guy, HFP tensor over S HFP, is free on one generator of degree 1. And another way to say this, analogously to this version 2 of Bökstedt's theorem that we gave earlier, is that you have an equivalence from HFP tensor sigma infinity of loops 2 S3, right? This is loops 2 sigma 2 of S1 to this HFP tensor over S HFP. And so if you had a suspicion that these two things are equivalent, then this already would motivate why you want to think about E2 algebras, right? Because this guy, it doesn't even have an E infinity structure a priori, right? Of course, once we know that it agrees with this, we could just transport the E infinity algebra structure over. But before you suspend and tensor with HFP, this guy is really just an E2 or maybe E3 algebra, but certainly not more, right? Loops 3 is not S3 is not like a twofold loop space, for example. So, and I mean, even if you had such a structure, just this guy is only free as an E2 algebra, right? So this is how this enters. And kind of contrary to what we said about the free E1 algebra earlier, this, like if you believe the lemma, then this already suggests to you that the homotopy of a free E2 algebra over FP is a complicated beast, right? For example, just the homotopic groups are not free on a generator in degree 1. So there's some additional structure of these E2 algebras going into the proof of this lemma. But before we prove the lemma, or rather see what we need to reference in order to prove the lemma, because there's of course, some calculations going into this at the end of the day, let's see how to prove Bökstedt's theorem from this. And I'm going to clean the board and then I can tell you. So now we're doing a proof of Bökstedt's theorem. More precisely, version 2. And we're assuming the lemma over here. So, and it turns out this is now really easy. So if we take THH of FP, we can write this as HFP tensored over HFP tensor S HFP. In the original formula there was an op here, but again, as for usual Hochschild homology, for commutative algebras that doesn't matter. You can identify the algebras HFP and HFP op. So that really just matters for associative algebras. So we have this, but now we said that we can rewrite this as this kind of free E2 algebra. And now you observe all of these terms come from spaces under this functor sigma infinity plus and then tensor with HFP. Right? This term comes from the space loops 2s3, and these two just come from the point. You take sigma infinity plus of the point, you get the sphere spectrum, and then you tensor with HFP, you get HFP. Right? So if you think about the bar construction that gives you this tensor product, you can form a corresponding bar construction of just loops 2s3 acting on two copies of the point. Right? It's the same kind of diagram with like points on the left and right, and then in the middle you have multiple factors of loops 2s3. And this functor, sigma infinity plus and then tensor with HFP, is symmetric monoidal and it preserves colimits. So what you see is that this guy, colimit of the corresponding bar construction, is just equivalent to HFP tensor sigma infinity plus of the corresponding bar construction in spaces. Let me just write that in this kind of classical way: bar point comma loops 2s3 comma point. So you're just thinking about the point as left and right module here. And now in spaces, there's a description for what this bar construction does. If you have an E1 algebra, a group like E1 algebra, and you take this kind of bar with respect to this acting on the point, then this produces a D-looping. This is one direction of the equivalence in the recognition theorem, that somehow connected spaces and group like E1 algebras are the same, where like the other direction is loops. So for this algebra, this just spits out loops S3, right? That's what we get by D-looping in this way. And so we recover the description that we gave for THH in Bökstedt's theorem, version 2. And now you can wonder, what about multiplicativity? But so basically, this is an E infinity equivalence, right? Like, that's not something that we checked earlier when we gave a proof sketch for this identification, but that's compatible with the multiplicative structure that you get from the cyclic bar construction or from the two-sided bar construction here. So this is multiplicative. And then here, this is still multiplicative, using the fact that if you take a bar construction over an E2 algebra, you still have this E1 algebra structure left. So this one way to think about this is that the bar construction kind of uses up one E1 direction, but you can think about E2 algebras as E1 algebras and E1 algebras. So you can perform this whole bar construction in the world of E1 algebras, so you still get an E1 algebra out of it. And so similarly, this guy still has an E1 structure, and that's compatible with just writing it as loops S3. So all of this is multiplicative, and that proves Bökstedt's theorem. And since Bökstedt's theorem looks so much simpler than this lemma we just input, I want to also remark that they are in fact equivalent. So if you had some other way to prove Bökstedt's theorem, you would actually prove this description of HFP tensor over S with HFP as an E2 algebra. And this is simply using, not lemma, remark, this is simply using the following fact. So Bökstedt's theorem and our lemma are equivalent, since map A to B of connected HFP algebras is an equivalence if and only if the induced map HFP tensored over HFP to HFP tensored over. So these two tensor products where we tensor over A and over B, respectively. So here connected simply means this is a connective HFP algebra, so it doesn't have negative homotopic groups. And the zeroth homotopic group is simply just FP, nothing else. And so if you have this statement, then, so we said earlier, we do have a map or I guess this is something that we will see in a minute, but it's not too hard to check. Since this guy, HFP tensor sigma infinity plus loops 2s3, is a free E2 algebra, we do get an E2 map from this guy into HFP tensored over S with HFP simply by specifying an element in pi1. So it turns out pi1 of this is FP. That's something that you can compute very directly. We'll talk about that later. And so you can specify a map which already is an equivalence on pi1, right? And now if you apply, so that's an E2 algebra map. And now if you apply this bar construction to these algebras, then on one side you will get the free E1 algebra on a generator in degree 2, and on the other side you will by definition get THH. And the map now you get is an iso on pi2 because this was an iso on pi1 and there's some connectivity statements. So if you know Bökstedts theorem, then you know that this map becomes an equivalence after doing this bar construction on each of the guys. So if you know that this kind of construction detects equivalences in this way, then you can use this the other way around. Bökstedts theorem implies that this map is an equivalence. I think that's a very fun fact. So this lemma here, that a map of connected HFP algebras is an equivalence if and only if it is on these bar constructions. That's not too hard to prove. So that's something I want to pose as an exercise, but it's a little tricky. So you have to think about how this bar construction, or I guess tensor product over connected algebras, how that behaves with respect to connectivity of the modules. So it's a relatively elementary exercise, but it's a little tricky. So let me pose that as a difficult exercise. Okay, so how do we prove the lemma that told us that HFP tensored over the sphere with itself is free if we just look at it as an E2 algebra? So we have to use some additional structure because, as we saw, the homotopic groups are certainly not just free as an algebra. But it turns out on the homotopic groups of EN algebras, you have additional structure called Dialashov operations. So let me focus on P, an odd prime here. There's some slight modifications one has to make for P equals 2, but the P equals 2 case is a little easier even because you don't have to distinguish between even and odd indices. And let me first talk about these Dialashov operations for E infinity algebras, because that's somehow the cleanest picture. So P is odd, and for an E infinity, let me write this down maybe. For an E infinity HFP algebra, there are the so-called Dialashov operations. And there's one for every integer I in Z called Qi, and it goes from pi n of r to pi n plus 2p minus 1 times I r. So they somehow raise degree by a suitable multiple of I. And closely related, there are also relations, operations beta Qi that have almost the same degree with an additional minus 1 here. So this times I and then minus 1. So these are so-called power operations. They come from the fact that you can understand in this E infinity tensor active category, the mapping spaces are certain configuration spaces, and you should think of these operations as somehow coming from the homology of configuration spaces. That's why you get these additional operations acting on the homotopy of your, on the FP, like on the homotopy of your FP algebra. So, these satisfy, in addition, that if you in-plug an element of degree n, then somehow Q n half, if n is even, right? Otherwise this doesn't make sense. So if n is even, then Q n half actually takes x to the p. So this is one reason why these operations are somehow also called power operations, because they're somehow related to the map that takes the p power. And also, you have Qi of x is 0 for I smaller than n half. And this is also valid for n odd, right? So the takeaway here is that somehow in the bottom degree where these are non-zero, in the even case, they're simply a special case, or like they're given by just raising to the power. And then in lower degrees, they're 0. And similarly, you also have the beta Qi x is 0 for I smaller equal n half. So you have these kinds of operations, and they satisfy all kinds of relations. So you can compute some really cool things using these operations. But we will be talking about E2 algebras, right? And so you don't have all of these. This comes from the fact that somehow not all of the classes in the homology of configuration spaces are already there if we just look at configuration spaces in 2 dimensions. Right? Somehow there's additional classes that come up when we increase the dimension of the surrounding space. So it turns out that on E2 algebras, we already have Qn over 2x for n even, and Qn plus 1/2 x and beta Q n plus 1/2 x for n odd. So these are already defined for an E2 algebra. And natural operations there. There's some subtleties. For example, these I think are not necessarily additive if we just plug in an E2 algebra, but that won't matter for us. We just want that we have these natural operations. Okay, and of course, I mean, this part is not interesting because, as we said over here, this operation, Qn over 2, applied to an degree 2 class, degree n class for n even, that's just another name for the operation that takes the pth power. That's something like we didn't need to know this to be able to take pth powers. We just need an algebra structure. But this is an interesting operation, right? It's not related to the pth power. In fact, I mean, if you take a pth power of an element of odd degree, then by graded commutativity, the pth power is already 0. But this guy somehow lives in higher degrees. It's not directly related to the pth power, right? So this is some additional structure that we have on the homotopic groups of an E2 algebra over Fp that we don't see just by looking at the ring structure of the homotopic groups. And so these were introduced by Dyer and Lashoff in a paper about the homology of iterated loop spaces. And so what they prove and this is, I suppose, inspired by kind of a previous work by Araki and Kudo for p equals 2. So they did something analogous there. And what they compute is that the homology of loops 2s3 with Fp coefficients. So let me remind you that this is the same as the homotopy of HFP tensor loops 2s3, this free E2 algebra that we're interested in. This is actually of the form an exterior algebra on a generator A, a generator Q1A, a generator QP Q1A, etc., tensored with a polynomial algebra beta Q1A, beta QP Q1A, etc. Using these operations 1 degree lower, beta Qi. Right? So they tell us that somehow the homology groups of loops 2s3 are generated by a generator A in degree 1 under these additional operations that we do have on the homology of an E2 algebra, on the homotopy of an E2 HFP algebra, such as this. So this does look very free again. I mean, it's not obviously free on these operations, but this comes from the fact that there are certain relations these satisfy. For example, when I compose two of these guys with a beta in there, there's going to be some relation. So there is actually a stronger statement than that where you talk about n-fold loop spaces of an arbitrary sphere, and then there's a statement that this is kind of freely generated by certain of these Dialashov operations under certain relations. So this is something that's understood. All right, so we're not going to prove that. This is an essential kind of computational ingredient. It does have to do with the fact that you can try and compute this with the Serre spectral sequence. There's some complicated pattern of transgressive differentials that are somehow related to each other via these operations. And let me not go into that. But that's the ingredient that we will need. And now if you look at this, this looks an awful lot like Milner's description of the dual Steenrod algebra. right? We have exterior generators, and we have polynomial generators. And you can even work out that the degrees fit together with the degrees of the tau i's and the xi i's. By the way, one thing I should have said is that, of course, these specific applications of QIs that I'm doing here actually are precisely these ones that are defined over an E2 algebra. So that's the only thing we're using here. Okay, so now how do we compare this to the dual Steenrod algebra, right? This looks very good. This looks like all we need to do is to somehow say something about how these elements relate to the tau i's. And of course, the dual Steenrod algebra is also homotopy of an HFP algebra. In that case, it's even an E-infinity HFP algebra. So you have all kinds of these operations acting. And these are in principle something that you can compute. There's some formulas that you can expand, and they give you a description of how exactly these operations act. And in particular, the ones we need have been worked out explicitly by Steinberger. So what he shows is that on the homotopy of HFP tensored over S with HFP, we have tau I is q p to the I minus 1, q p to the I minus 2, etc. q1 of tau 0, and xi is beta q to the p to the I minus 1, q to the p to the I minus 2, all the way down to q1 tau 0 again. Right? Just as a reality check, note that the xi had degree exactly 1 less than the tau I, and in fact, of course, like this beta q guy has just degree 1 less than this guy. So the degrees somehow check out, and this is something that one can prove. It's again something that we won't prove here, but it's something that can be explicitly computed. All right, now all that's left to do is to somehow construct a map that uses these descriptions to show that we have an equivalence. So what goes into that? Well, let's finally prove the lemma, by which I mean the main lemma, this E2 description of HFP tensor HFP. So first of all, this is something I already announced earlier. If we want to compute pi 1 of HFP tensored over S with HFP, then this guy maps, of course, to the corresponding tensor product over the integers. Right? That's just because the action of S on HFP, it factors through HZ. Right? So this maps to HFP tensored over HZ with HFP. And this now, this is something we can explicitly compute, right? Because HZ modules, as we said in the previous lecture, HZ modules, or 2 lectures ago, HZ modules are really equivalent to the category DZ. And so what we're computing here is just a derived tensor product of FP with FP over HZ. What's over Z? And what's the first homotopic group of that? Well, it's going to be the first homology group of the derived tensor product, meaning it's a Tor 1. tor1 of fp comma fp over z. And of course, that's just fp. Alternatively, you can just copy the argument that you use to compute tor1, which is you resolve fp by 2 copies of z, and then tensor. You can just do that on the level of spectra. You can write down a cofiber sequence where you have hz, hz, and hfp, and then if you tensor that and you use that cofiber sequences are turned into cofiber sequences, you can also just get this pi1. And now the crucial fact here is that for connectivity reasons, using the fact that the map from S to HZ is like one connected, you can check that this map is an isomorphism. So let me not say anything more about this, but rather pose as an exercise to compute this, right? Either using this and this kind of connectivity argument with S and HZ, or you can also, for example, input some statements about the low degree homotopic groups of the sphere and try to directly resolve this HFP by some cofiber sequences over the sphere. I think it's a pretty good exercise to get some working feeling of how to work with these spectra. So now that we know this, well, we get a map of E2 HFP algebras HFP tensor sigma infinity plus loops 2s3 to HFP tensored over the sphere. HFP corresponding to a chosen generator in here, right? Just pick any. But of course, there's canonical ways to describe elements in tor1. We could also just fix one. So this is going to be a map which on H1, on pi1 of this, pi1 is H1 of loops 2s3, by, for example, by this computation, that's just an FP in degree 1. So this map is going to be an isomorphism by construction on pi1. And now, here comes the crucial part. This is an iso on pi1, but both sides are generated in the same way by the E2 Dialashov operations. When I say generated in the same way, then all I'm saying here is that, well, A goes to some unit multiple of tau 0. So Q1A goes to some unit multiple of Q1 tau 0, which is tau 1, and so on. So all of these go to the tau I. These guys, by this description here, go to the Xi, and then this is exterior algebra on these guys, tensor polynomial on the other guys, and the other side has the same description, right? This is literally an isomorphism that just identifies the generators, just gives them other names. So this is an iso. And an isomorphism, if you have a map that induces an isomorphism on homotopic groups, such as this one, then it is an equivalence, right? So this is by construction a map of E2 HFP algebras, which is an equivalence. And equivalences between EN algebras are detected underlying. So if you have a map of EN algebras that's an equivalence on underlying spectra, then it's an equivalence. So this finishes the proof of our lemma. And by that, it also finishes the proof of Bökstedts theorem. So let me finally say that, of course, you can also do the same thing for p equals 2, and then the corresponding description due to Araki and Kudo tells you that it's polynomial on certain p equals 2 Dialashov operations. And the p equals 2 Dialashov operations have a slightly different indexing than the odd primary ones. You don't get these beta guys, and the degrees are a little different, but turns out to match up exactly with the fact that the dual Steenrod algebra is just polynomial in that case. All right, that does it for today. Thanks for watching, and hope to see you next time.